So we want to continue with the product and quotient rule, but I want to look at this situation here. We've been looking at the quotient rule in the last video at the end, and here certainly is a quotient. Okay, take the derivative with respect to x of this thing. This is a quotient. Now, certainly we could use the quotient rule, but we don't have to. We can simplify this first. And I think it's actually a little bit easier to deal with as far as the simplification goes afterwards if we simplify first. Now, the simplifying first is a little bit of work, but it's not going to be that bad. So let me explain. Before I take the derivative, so I'm going to keep the derivative out here. Take the derivative again with respect to x is what this is saying. That's what that d over dx means. And of course, the square root of x. So you know, first of all, recall that the square root of x is x to the 1/2 power. So what I'm going to do is, this is x to the 1/2, but it's a single term again down here. So remember what I can do with that? I can divide every term in the numerator by this one term. It's the distributive property, right? It's the distributive property. Right? It's dividing each one of these things. You know, you can think of it as dividing by x to the 1/2 is the same as multiplying by 1 over x to the 1/2, and then I distribute that through multiplication, right, to each one of these. And so each one of these then can be further simplified by the rule for exponents, right? When I'm dividing, what do I do with the exponents? X squared divided by x to the 1/2, I subtract the exponents, right? So this will be what? 2 minus 1/2. That's 1 1/2 or 3/2. I'm going to leave it as 3/2. Don't write mixed numbers. 1 1/2 is too cumbersome and confusing, so write it as an improper fraction. Here I get x to the first divided by x to the 1/2, subtract the exponents, I get x to the 1/2. 1 minus 1/2 is 1/2. And then here, well, 1 over x to the 1/2, that's just going to be what? Minus x to the negative 1/2. That's the reciprocal of x to the 1/2, so I can write it that way. So again, this is pure algebra in the simplification. Not too bad, but now what do I have? I don't have any quotient rule. I don't have any product rule. I just have sum, difference rule, constant multiple rule, and power rule. That's all I have. And so we can take the derivative, right? The 3 is a constant multiple. What's the derivative of x to the 3/2? Power rule. Bring the 3/2 down. Subtract 1 from 3/2. 3/2 minus 2/2 is 1/2. Constant multiple, pull that 2 out. Derivative of x to the 1/2 is power rule. Bring the 1/2 down. Subtract 1 from 1/2 is negative 1/2. And then here, bring down the negative 1/2. X to the what? Subtract 1 from 1/2 is negative 3/2. And then I just clean this up. I get 3 times 3/2, that's 9/2. X to the 1/2. Plus what? 2 times 1/2 is just 1. I'm left with x to the negative 1/2, which I'm going to rewrite as 1 over x to the positive 1/2. And then minus a negative is plus 1/2. X to the negative 3/2 becomes x to the positive 3/2 down below, right? And here it is. Now I could combine this as one complete fraction, and if I did, that's probably closer to what you would get if you used the quotient rule right out after simplifying. But I'm going to leave it just like this. Okay, so that's a good form to be in for right now. We've taken the derivative, and I didn't have to use the quotient rule. Quotient rule, you get quite an ugly looking expression doing the quotient rule with this, and you would, you know, if you wanted to simplify it to this, you would have to do a lot of work. So again, the idea is if you can simplify first, right, then do so. Now sometimes instructions might be, you know, use any rule you want to find the derivative. Then, you know, obviously simplifying first would probably be better. Now if it says, you know, you have to use the quotient rule, then of course you would have to use the quotient rule to show support. But a lot of times I may ask, you know, find the derivative without using the product or quotient rule. And then you know you have to simplify first. Okay, so But the idea again is, think about that. There's more than one way to go with this, but I think this is the way you want to proceed. Let's do one more example with the quotient rule with some constants. A, B, C, and D are constants here. This one I can't simplify, right? Since I'm dividing by CX plus D, it's not a single monomial term. There's a binomial down there. So let's find the derivative with the quotient rule. Let me just remind out here, this is without quotient rule. Okay, this one is with quotient rule. So what do I have? The derivative y prime, I'll just say, derivative of the top function, remember a and b are constants, times the bottom, minus the top function, times the derivative of the bottom, all over the bottom function squared. What's the derivative of ax plus b? Remember a and b are constants. Derivative of b, constant, is 0. A times x, derivative is what? A. Equal to a, right? So it's just a line of slope a. Over here, the derivative of cx plus d is going to be c. So if I distribute this a over the cx plus d, I get a cx plus a d. And then here I get minus ax times c is minus a cx. Minus b times c is minus bc. And notice ACX minus ACX is 0. This simplifies down to just AD minus BC. And there's your derivative in terms of the constants A, B, C, and D. All right. Let's do a few more examples now. Now that we have the product and quotient rules, we can find the equation of the tangent line. Okay, so let's practice doing that. Let's find the equation of the line tangent to the graph of this function at x equals 0. Okay, well, notice this is a product. Now I could distribute e to the x through, but I would still have products. In fact, I would have 3x squared times e to the x would be one product, and 4x e to the x would be another product. So I'm going to leave it factored like that. I'm just going to go ahead and use the product rule, because in order to find the equation of the tangent line, I need the slope of the tangent line. And what's the slope? It's the derivative of the function. Of course, we're finding the slope of the tangent line, finding the equation of the tangent line at x equals 0, so we need to find f prime of 0. So first I have to find f prime, and it's by the product rule. So I take the derivative of the first function, which is all of this stuff, times e to the x plus all of this stuff times the derivative of e to the x. Right. Well, what's the derivative of all this stuff in here? What's a nice little polynomial? That's easy. The 2 comes down, times 3 is 6x, subtract 1 to the first, the derivative of 4x, 4, derivative of 2, a constant, is 0, derivative of e to the x is just e to the x. Okay. Now, I could simplify the derivative, distribute e to the x through, distribute e to the x through, combine like terms, simplify. I'm not even going to do that. Because I'm not asked to find f prime of x. I mean, I found it, essentially, but I don't have to simplify it. I'm trying to find the equation of the tangent line. And all I need is the slope. Let me just evaluate this, at 0 to find the slope, right? That's the slope. And notice when I plug in zeros, things disappear. 6 times 0 is 0. This becomes 4 times e to the 0, right? Plus, if I plug in a 0 here, what does that become? 2 times what? E to the 0. It's a total of 6 e to the 0. What is e to the 0, by the way? It's 1. So this whole thing is 6, right? And that is my slope. Right? That's the value of m. What else do I need? I need the point of tangency. What's the point of tangency? Well, we're talking about when x is 0, so it's 0 comma what? F of 0. Right, f of 0. So I need to find what's the y-coordinate for this point, right, on the original function that the line is passing through. So I plug in 0, and what do I get? 0, 0, I get 2 e to the 0, which is equal to 2 times 1, which is 2. And so remember the point slope form, y minus y1 is mx minus x1. So I can now plug in y minus y1, this is y1, which is 2, equals m, which we found is 6, x minus 0, right? In fact, I could have went right to the point slope form because 0 comma 2, that is the y-intercept. I can go right to the slope-intercept form, rather, in this. But at any rate, I think you see this, I get y minus 2 is 6x, or y is equal to 6x plus 2. And I'm sorry, I could have went right there because I know the slope is 6 and I know the y-intercept is 2. So, at any rate, again, I have the equation of the tangent line. And don't forget, we can check by graphing the original function and then the tangent line and seeing if it looks tangent to the graph. Now, this graph might look a little bit hard to try and see that, especially if it's real steep at that point. It's got a pretty steep slope of 6, so it might be hard to see that a little bit. You might have to open the window up to visualize that on your calculator. Okay, do another one. Let's find the equation of line tangent to the graph of this function at x equal 1. Well, now I have a quotient here, so if I'm finding the derivative, do I have to use the quotient rule? Well, in this case, yes. I could use polynomial long division to simplify this. I mean, be my guest if you want to do that. You're still going to have a little quotient rule at the end, though, to deal with. So I'm going to go right into quotient rule. Derivative of the top times the bottom minus the top over the derivative of the bottom, all over the bottom squared. By the way, you know, I never square out this thing in the bottom. I leave it just like that. You know, it doesn't really help to simplify by expanding that out. What's the derivative of 11x squared minus 3? Bring the 2 down, I get 22x. Derivative 3 is a constant, I get 0. What's the derivative of 5x squared minus 1? 2 times 5, 10x to the first power. Again, power rule is going on there. Now, I am going to simplify this down. I know I didn't simplify the last derivative, but something nice happens. 22 times 5, can you do that? 20 times 5 is 100. 2 more 5s is 10, so that's 110. X what? X times x squared, x cubed. 22x times a negative 1 is just negative 22x. And then here I have minus 11x squared times 10x. 11 times 10 is also 110, so it's minus 110 x squared times x cubed. Hey, see how I can simplify here? Then minus times minus is positive 3 times 10, 30x. $110x cubed minus 110x cubed is 0. I get negative 22x plus 30x is 8x. So I just went ahead and simplified that down a little bit. And so what's my slope? It's h prime of what? Where am I finding the equation of the tangent line? At what? X equal 1. So I want x to be 1. So I plug in 1 here. And up top I get 8. What do I get down here? That's 5 minus 1 is 4. I get 4 squared, which is 16. I get 8/16, which is 1/2. So my slope is 1/2. What's my point of tangency? it is 1 comma h of 1. And h of 1 is equal to what? So go back to the original function here and plug in 1 for x. And simplify, get 11 minus 3 up top, which is 8. And down below I get 5 minus 1, which is 4. I get 2. And so my equation is y minus y1, which is my y-coordinate, my point of tangency, 2, is m, which is 1/2, x minus x1. And I'll let you solve for y in this, and you should be getting y is 1/2 x plus 3/2. And there is the equation of our tangent line. So we've come quite a long way to being able to find the equation of the tangent line. And product rule and quotient rule help quite a bit. So that limit definition of the derivative that we've been using is in the background, but we're not using it anymore to find the derivative. We're directly, at any rate, we're using what we determined from that. Okay. Lots of algebra going on, so again, you've got to be good at algebra. You've got to be good at simplifying things. You've got to be good at evaluating and simplifying these expressions, factoring, etc., etc. But I can give you some graphical examples as a crutch, so to speak. These are good questions to make sure you really understand the process. So here's the way I do that. I give you the graph of two functions here. G is the solid line. You see G is this solid line. Okay, and H is the dashed line. It's basically some kind of piecewise defined function. It's got, linear segments. It's got some sharp turning points, which you should know something about the fact that it's not going to be differentiable at those points. So like G is not differentiable at what? -1 or 2 or 4. And H is not differentiable where at -3, -1, 1. Or 4, and so you've got those issues. But you should be able to estimate the following values. What is G of 3? So this is not even calculus, this is pre-calculus. What's G of 3? So I go to x equals 3, G is the solid line, go up to that point, and what's the y-coordinate? 1, G of 3 is 1. But what is G prime of 3? What's the derivative of G at 3? What's the slope? Well, at 3, what's the slope of this function? Well, it's just a line. What's the slope of a line? It's what? We just see what we go from one point to another. What do? I go down 1, 2, 3 and over 1. Down 1, 2, 3 and over 1. So the slope of this line segment is what? -3. And therefore G prime of 3 is -3. So I've made it easy. By making these all linear segments, you should be able to determine the derivative at any point, if it exists. What's H of 3? H is the dashed line. At 3, what's the value of the function H? It's -1. H of 3 is -1. What's H prime of 3? What's the slope of this line segment? Because we're talking about the derivative right at that point. So what's the slope of this line segment? It looks like it goes down 2 over 1, down 2 over 1, right? So it's a slope of -2. Right? So from this, right, I'm not asking you to come up with a formula in this question down here. It says if f of x is g of x times h of x. I'm not giving you, you could actually write out the formula equation for each of these line segments. I think you can, right, because each one you can determine the slope, you can find the point, you can get the equation, right? But I don't want you to do that here. But I do want you to say if f of x is the product of g of x times h of x, I do want you to find f prime of 3 without coming up with formulas for the actual functions themselves. Say, how can I do that? Well, in this case, how do I find the derivative? I use the product rule, right? So the derivative of the function f is what? Product rule. Derivative of the first function times the second plus the first function times the derivative of the second. Okay. Now, someone might say, well, it has to find f prime of 3. You found f prime of x. Well, yeah, I did find f prime of x. You've got to find f prime of x first before you find f prime of 3. You don't want to plug 3 in first and then take the derivative. If you plug in 3, you're going to get constants. And the derivative of any constant is 0. That's not the way we find the value of a derivative at a point. We don't plug in and then differentiate. We differentiate and then we plug in. So I found the derivative. Now I can plug in what's f prime of 3. It's g prime of 3 times h of 3 plus g of 3 h prime of 3. And I'll just have you note, each of these values we have found from the graph already. All right? So we're just going to use the graph to estimate these values. G prime of 3 was negative 3. H of 3 was negative 1. G of 3 was 1. H prime of 3 was negative 2. Negative 3 times negative 1 is 3. 1 times negative 2 is negative 2. Add them together, I get 1. There's my answer. F prime of 3 is negative 1. Or it's positive 1, rather. I don't need to find formulas for the functions G or H. Let's do a couple more of these with the same set of functions, G and H. This time I'm going to define a function p of x, which is x squared times g of x. G of x is this solid line right here. Okay, let's find p prime of 2. Well, we first have to find p prime of x, right? Find the derivative first and then plug in. Well, here I've got x squared times g of x. So this will be the derivative of x squared times g of x plus x squared times the derivative of g, which is just g prime of x, right? What's the derivative of x squared? That's pretty easy. You should know that. 2x, right? So there's my formula for p prime of x. So p prime of negative 2, I replace x with negative 2. I get 2 times negative 2 times g of negative 2. So I've got to evaluate g. Remember, this is not multiplying g times negative 2. This is g of negative 2. Plus negative 2 squared g prime of negative 2. Okay. So I go to the graph. What is g of negative 2? G is the solid line. So I go to where x is negative 2. What's the output? 2. The output is 2. So g prime of negative 2 is 2. What's g prime of negative 2? That's the slope. What is the slope of the graph at negative 2 for the function g? Well, guess what? What's the slope of this line right here? It goes what? Up 1, 2 over 1. Up 1, 2 over 1. Its slope is 2. So that's also 2. Okay. So again, I'm estimating these values from the graph. This is the value of the function. This is the value of the slope of the function at negative 2. So now I can just do the arithmetic. 2 times negative 2 times 2 is negative 8. Plus, this will be positive 4 times 2 is positive 8. And I get 0. Let's do one more example. Guess what we're going to have to use here? Looks like a little quotient rule. Right? Looks like a little quotient rule. So, how do I find the derivative? With the quotient rule, right? I'm going to find q prime of negative 4, but I've got to find q prime of x first. Right? So I'm going to use quotient rule. So it's the derivative of the top, which is h prime of x, times the bottom, which is 5x, minus the top, times the derivative of the bottom. What's the derivative of 5x? What's the derivative of the bottom? 5. All over the bottom function squared. So this is quotient rule. Right. So you got to be careful with arithmetic too. It's the bottom function squared. We're squaring 5x. So it's 5 times 5, 25x squared in the bottom. Now here I've got 5x, h prime of x, minus 5 h of x. I'll just bring the numerical part in front each time. And there it is. I'm not going to simplify this any further. I'm just going to go right in and now find what I'm looking for, g prime of -4. So be careful, it's a -4. So everywhere I see an x, I'm going to replace it with -4. Okay. Now, what do I need? I need to know what h prime of -4 and h of -4 are. So let's go to the graph of the function again. H was this dashed line. So what is the value of the function at -4? At -4, the output is what? 1. Okay. So that means that h of -4 is 1. H of -4 is 1. What's h prime of -4? H prime is the slope at -4. So right here, what's the slope of this dashed line for this segment? What's the slope of this dashed line? It goes down 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. Slope is -4. Slope is -4. So our derivative is -4. Oops. Our derivative is -4. So let's do the math here. 5 times -4 times -4. -4 times -4 is positive 16. 16 times 5 is 50, and 30 is 80. Minus 5 times 1 is 5. All over 25 times 16. -4 squared is 16. Now 80 minus 5 is 75. Instead of multiplying 25 times 16, notice what we can do first. There's a common factor of what? 25. Divide numerator and denominator by 25, and I get my answer, which is 3/16. Okay. So those are different types of problems that you can expect to see in the homework involving the product rule and the quotient rule, but you see also involving all the other rules that we've been learning, and there'll be a cumulative effect. So we've learned now what? Constant rule, rule for the general exponential function, sum difference rules, constant multiple rules, power rule, we've learned product rule, we've learned quotient rule. Okay? So we're going to continue on, and we will be looking at higher order derivatives, and then we will resume our journey in finding derivatives of different functions.